Now, what a freshman. We're going to do today's start concept 55. Concept 55 is extremely important. It's the last 3 or 4 concepts we're doing, 55, 56, 57. And all 3 of them all show up a lot in pre-calculus, in statistics, in calculus, all these topics. Now, we have 3 more to go. 1, 5, 6, 57. I'll say it one more time. So, what we're going to do is define another constant today. Okay, we're going to define another constant, just like pi is defined. Who remembers, how is pi defined? No, that's not its definition, that's its approximate value. I asked how it's defined. 2 different questions. Victoria? Something about a circle, absolutely. Something about a circle. I saw a hand somewhere.
Something about the circumference.
Something about the circumference.
That weird number. What did we learn?
You know, last year in geometry, we talked about where pi came from and why it was invented.
Isn't it from the radius? Half of the radius?
Close.
It showed the board.
Circumference of what? You guys are all like half on the right track. If you remember that formula, circumference equals pi times diameter? Pi was really thought about as the ratio of the circumference to the diameter. And if you think about it, just divide by d, right? Divide by d, what do you get? You get pi. Pi was circumference over diameter every time. And after looking at many, many circles and the circumference of each circle and its diameter, the ratio kept occurring. 3.141526, so forth and so on. So that was where pi really came from. It was defined as, the definition of pi was defined as the ratio of circumference to diameter. Today, what we're going to look at is this new constant called e. And e is not a variable. Again, it is very, very rare that you're going to see from this point on a lowercase e used as a variable. Okay, just because e is also a number, it's a constant. And that's what we're going to look at right now. It's called the exponential constant, or the natural base. Okay, the natural base, that's the title here. That has to do with exponential growth and decay, which is what we've been studying. So, e is defined as the limit of this quantity here. And you might say to yourself, all right, well, that doesn't help me too much. Where does this number actually come from? What does the limit as n goes to infinity mean? Or what does as something goes to infinity mean? It's getting what?
Bigger.
Bigger, right? Bigger and bigger and bigger. So if you took a data table like this, you put n there and you put 1 plus 1 over n all to the n power, like that in the other column. And you kept increasing the value of n, what would happen here is this would get asymptotically closer to this quantity right here. Who remembers the word asymptotically? What does that mean, or asymptote?
It's like getting closer to it's gonna get closer to never get there.
It's never gonna what?
It's never get there.
It's never gonna get there, yeah. It's gonna get closer, but never get there. Go ahead.
It's like 2.718. I think it's going up from high school.
You think it's going up? I think so too. I think you're probably right about that. I mean, you never know though. Let's see what happens here. Maybe it comes from below. You never know. If I plug in a 0 here, what's anything to the 0 power? But what's the problem here? What's 1 over 0 going to be right here?
0 and undefined.
Undefined. So if you type this in your calculator, you're going to get error here. Okay, you're going to start with that one there. Because when you plug in that 0 there, 1 over 0 becomes undefined. Okay? But if I go anything beyond that, so if I start with a 1 now, let's plug in a 1. 1 plus 1 over 1.
1 plus 1.
2, right? To the 1 power, still 2. Try 1.5 in your calculator, see what you get for that. Plug in a 1.5, write it over here and over there, in these 2 spots. So again, you're plugging in a 1.5 right here and right here, and see what you end up getting for those 2. Remember, PEMDAS, PEMDAS, PEMDAS. If you're going to type this directly in your calculator, you also need parentheses around this part. What do you got? 2.15. So, as Trayvon mentioned, it is getting larger, the quantity, as n gets bigger. And what you're going to notice is, try another number like 10 now. Jump a little bit. Jump up to 10 and see what happens. And by the way, you don't have to type this in every time. If you put this in y1, you can just use the table function, obviously. If you put this in y1, instead of n, call this x. You can type that right into y1 and use the table function to do what I'm doing here. If you get 10, Try 25 after that. What do you got for 10? 2 point for 10? Try that again. Possible, it's right. Let's try it again. 2.59, thank you. I didn't think it was going to jump up that high that quick, okay. And 25? Again, guys, you could use your table function. You can use your table function. You can write this little table in the margin on the side. That's fine. Okay, just put it in the margin. 6.
Bar. 6 bars.
Okay. Now, as n goes to infinity, so we need to think of really large numbers to show that this actually goes to 2.718 ... right? So jump automatically to 100, please. Okay, if we jump all the way to 100, 2.704. Okay, we're getting closer and closer. Now, as we go on and on forever, and if you look at the graph of this function on your calculator, here's what you're going to notice it looks like. You're going to notice that, let's see, at 1 it's 2 right here. This line is going to go like this. That's what's going to happen. And this is going to be the quantity E, or 2.718 ... Okay? And this function will continue this way. It's going to continue that way also.
It's a math joke.
How come it looks so crooked?
How come it looks so crooked?
Yeah. Isn't it supposed to like curve really deep?
This is not exponential growth or decay. This is the function right here, Jason. This is the graph of whatever this quantity is right here I'm showing you. And as this goes on forever and ever, it's going to get closer to this quantity E. That's why this number is getting closer to 2.718. And as this number gets larger and larger, you're going to get to the approximate value of E. Okay? Say again? So you must have a typo in there somewhere. You got to figure it out.
No.
Yes. Are you showing me something?
No.
And we're only looking at which branch now. Right hand branch, right? Okay. And if you notice, Louise showed us the actual graph ends up looking like this here. It's like a rational function, you see. But again, we're only looking at the right hand branch. Okay, only the right hand branch. Okay, stop talking, please. Because you're all asking questions in that area. I'm not going to answer anymore if you keep talking. Please.
For the second part, it just starts right there, or is it like,
Well, there's a discontinuity. There's a vertical asymptote there. Because of the fact that this is 1 over 0, right? When I plug in n equals 0, do we get the error there? That's the vertical asymptote right there. So you're seeing like a rational function like we talked about. Okay? It's just a jump in the graph. So the idea of E is that E is really defined as some limit as n gets bigger and bigger. Now, before we get into the next stuff, and I'm going to just give you a little preview of what we're going to do. Remember the other day we looked at interest and we said compounding? We talked about compounding quarterly, annually, monthly, yearly, weekly, and n equals 52, or n equals 12, or n equals 4. Think back to the notes from last class we talked about. As n gets bigger and bigger and bigger, what did n have to do with when it came to compounding for interest or for money? What did n really mean? Say again? It's like the period of time, very good. It's like the period of time. As n got larger, what did that actually mean to those problems? For example, if n was 5 versus n being 52, or 2 was close to 8. What did that actually mean? It's tough. We got to think about what these actual terms mean here. What was n defined as? You have notes, right? You're all staring into space right now. Okay, you go back to your notes. We just did this in concept 54. That's why I'm asking this. It should be fresh in your mind for study this weekend. We also did stuff with A, R, and X, but we had an N in there in one of our problems. It was toward the end of our notes. Very good. Number, say level M.
It said the number of compounds.
Compounds per year. Compounds per year. And what that meant was, remember the person that is like looking at your money or doing your investments for you? It really means like, how many times a year are they really accruing your interest or analyzing your interest? So for example, if you are compounded twice per year, it's like they're looking at your interest or your investment in two different portions, one half a year and the other half a year. If you are investing at a monthly compounding rate, that means 12 times per year, they're going to analyze your investments to see your interest. Now, as n gets larger and larger, we get toward like daily compounding, which is when n is 365. Every single day, your interest is analyzed. Now, what happens if we want to do more than that, more than daily? I don't want to try using values event like 1,000 or 10,000, but that can happen. So what happens is we call that, as n gets larger and larger, as n goes to infinity, we call that continuously compounding. So what we're going to do today is we're going to look at two things. We're going to look at exponential growth and decay, but then we're also going to look at an application of it to do with interest. And it's one of the most common interest rates that you're going to see. That's why we're going to go into that today. And that has to do with this definition right here, as n goes to infinity. That's where it's going to come up as well. Okay, and n in this case is some dummy variable, it's called right here. Not dummy as in that, but dummy just means any variable. Whereas n in the case of investments had to do with the number of compounds per year. And we'll see how that relates. Okay? Now, what I did was, for this one, I put a little history of n on here, or of e on here. And you'll see that on your worksheet. It just talks about the discovery of it, and it's very interesting to look at. Because even before Bernoulli was credited for this, there were several mathematicians that used this function e, or had defined it without even realizing they'd done it before. Okay, so they came up with this number, 2.718, it kept occurring over and over again, and they couldn't figure out what it really meant until Joseph is his brother, Jacob Bernoulli defined, there were two mathematician brothers, Jacob and Joseph. So Jacob defined the quantity e as this limit. Okay, he defined it. And then you'll see that later on it was actually used or known to be used. Euler used it for a long time. By the way, this is actually called Euler's constant, in case you're wondering. It was titled Euler's constant, which some people might not agree with, because Euler was not the first person to come up with it, but he introduced it when he got into what's called logarithms, which is our next topic. 56 and 57 is that thing called logarithms.
You missed Jenkins.
Is Jenkins doing logarithms?
You
You did with logs already?
Yeah.
Hey, look at that. All right. See, you remember how we switched it up? Normally we do it first here. Remember how I switched up?
Guys.
Separate yourselves, just stop. Remember how I switched up for the SAT earlier in the year so that we did this stuff on statistics earlier, so it was ready for your SAT? Normally I do this first. So last year I remember we did this, and then you did it, or they did it afterward in chemistry. But that's good. You got a preview of it, because we're going to get into that in the next 2 days. It's a very easy topic. It's just rules. That's all it is. If you can follow rules, you'll be fine with logarithms. Okay? You're just going to be told these are the rules of them, this is how they work, and so you're going to analyze them. There's just a bunch of rules right after each other. All right. Let's get into some applications of these. So you have this in the bottom of your page also. So the first page is pretty much just a read off of it and take some little notes here and there. First, remember the exponential growth and decay function? We talked about this last class in concept 54, where A was what again?
A is the
Starting value, or the initial quantity. What was R?
the rate, like the year.
The rate, that's fine. Not the year, the rate. The rate. Per year, you could say, or per day, or whatever. What was X? Good. Time intervals passed. Time intervals. Whether it's hours or years, depending on what the rate was. Same years. So we had that from last class. Now, instead of that, we can think of this as A e to the Rx. Now, A e to the Rx. This is very similar to this last one, but instead of compounding per unit time, remember it was like 2% per year was the interest rate. Or if the growth or the population decayed at the rate of -3% per day or per year. Because, you know, for example, let's think about predator-prey. Predator-prey models. What are some predator-prey models you've heard of before? And whether it's biology or physical science. And I mean, predator-prey, like, what's an animal that eats another animal, pretty much? That's what I'm asking. What is it? Cheetah eats zebra. Okay, cheetah eats zebra.
Humans
Now-
eat humans.
At a certain point in time,
That's why we were very good.
at a certain point in time, the population is going to start to decay, right?
Animals and cats.
So, say there was an island, okay? So you've got an island, and you might want to think about this idea of what we're talking about now, because it's going to come up again. I'll tell you next.
Darwinism?
You have an island, and on the island, all you have are zebras and cheetahs. Okay, and obviously a lot of plant life. So the zebras are happy to eat plant life, they eat their plant life, and they get along. But the cheetahs, what do they want to eat? The zebras. Okay. So say there's like 100 of each on the island. Now, after some time, what's going to happen to the populations respectively?
They're proportional.
Zebras will go what?
Decrease.
Up. It'll go up.
Decrease.
Oh, it'll change.
Cheetah will
It'll
go
go
up.
up. It'll stay
Why are we
constant.
saying up and down? What are some arguments? Give me an argument first.
Isn't it because the cheetahs would eat the zebras? And
Cheetahs will definitely eat the zebras, so the zebras might go
down.
down right away. And they might reproduce, go back up, absolutely. So they will fluctuate a little bit, right?
Yeah.
But over time, the general population is going to go down because they're going to keep eating them.
No,
Well, the
it's
zebra-
because
isn't the
when
cheetahs gonna go
a big
up?
cat eats one of like deer looking things. It's like enough food for them for a year.
Or some of the cheetahs.
Okay, but we're
are
talking,
intense.
yes,
It's
absolutely.
enough food for them for a year, so they wouldn't eat it another one.
There might be like 10 of them to give in on that. But again, let's say we're talking about a long time period, Jason, a long time period. So the general population of the zebra will go down, whereas the population of the cheetah might go up initially, right? They might have enough food, they might reproduce, so their population will go up. But over time, if the zebras run out, what's going to happen to the cheetahs? They're also going to eventually start to die, right? So you have some ideas of growth and decay. Now, we're not looking at per year. What we're going to be looking at today is instantaneous rate and decay, rate of growth and decay. So instead of looking at this quantity here, we're now going to look at this quantity. And remember that the value of r, or when r was greater than 0, we had growth. And then when r was less than 0, we had decay. That was for this quantity here. It's the same thing now. So if you notice that r is positive right here where I'm pointing, right there, then it's going to be growth. If you notice that r is negative, it's going to be decay. Again, the same thing as last time. When r is positive, we have growth. When r is negative, we have decay. Now, for this function, we're good. For this function, it's written like this, as we showed a minute ago, but a lot of the time, it's actually written like this, right over here. Instead of an x, a t is automatically introduced. Because a lot of these functions are functions of time. They change with time. They are dynamic functions. What does dynamic mean? Versus static. Static versus dynamic. Changing for dynamic. Static is staying the same or unchanging. So this function y, or the quantity, is usually a function of time. It is a dynamic function, okay, because it changes with time. Now, the variable a still dictates the concavity and the starting point, just like we discussed in the last part. Okay, so it doesn't change. So your simple example of growth when it comes to these functions is just e to the x. And decay is e to the negative x. So we still have growth, we still have decay. No different than what we've had before. All we're going to do now is look at different applications of it. So let's go to our first example now. So example 1. At the start of an experiment, there are 100 organisms. So it could be humans, it could be amoeba, it could be just normal red blood cells, some organisms. If the population follows an exponential growth pattern with a rate r equals 0.02, what is that in percent, by the way? 2%. Okay, just so we're clear, that is 2%. Let's give it as a decimal, though. And time intervals are measured in hours. A, what will the population be after 5 hours? And B, how long will it take for the population to double? Okay, what will be in 5 hours? How long will it take for it to double? Can I ask somebody to please give me a function based on what we just looked at that would fit this? So think about what A and what R is and write a function on your paper based on what we just used for our general function a minute ago. Remember that our general function was looking like this in the green box right here. That's what we were talking about. Using that function there, write a function for this problem that gives a general representation. So this is another function that's continuous, and this is the same thing as that. traditional x-axis this time. Again, what I want you guys to do before we even begin part A is just write the general function out. Okay, f of t, whatever the function may be. What is the a value in this problem? Why is it 100? It starts at 100. The starting value, good, it's 100. Now, for this kind of a problem, we're going to say, all right, well, it's a times e to the r t. That's the general function. Now, many of you plugged in for t already, obviously, which I agree with. So for part A, what are you going to plug in for t? So we're doing f of 5. And we get 100 times e to the 0.02 times 5. Is it negative? Let's see. It says follows an exponential growth pattern. So when it's growth, it is positive, positive, positive. When it's decay, it's negative. That's decay, it's negative. What are we end up getting here? Round to the nearest organism. Remember, people, there's an E on your calculator. Sorry, I should have mentioned this. Whoops. To find the E on your calculator, it might be useful to actually know where it is. Hold on. Sorry about that.
It says syntax.
Yeah, because you don't use the E like the letter. I'll show you where the constant E is on here.
Yeah, little E right there.
Is there a what? It's probably right near the log sign, I think, usually.
It's right underneath the leaf.
It's over the division sign.
Okay, there's two spots. First, E is right here by itself, like Jason said, above the division sign. But there's also E down here, above the natural log sign, ln.
E to x.
And you could plug in your exponent then. So like you could do, watch, 100 second e to the x, and then just put 0.02 times 5 in there. Okay, that's one way to do it. Another way to do it is simply just plug it in y equals, please. Do this. Go to 100 second, then I press this e over here, and I put 0.02 x. Close parentheses. Now I can go to my table if I'd like to. And what's my x value I want to plug in again? 5, right? I just hit 5, hit enter. I get 110.5. Does that make sense? It's logical.
Where'd you put it?
It's right here. It's all, guys, you can see my y1 is right here. There's my y1, and then I'm plugging in the table.
How come I got 106?
It's a
Oh, wait, never mind.
calculator.
I'm number 3.
Try that again, it probably worked. So again, the function is right here, you can see that. Okay, the function is right there, and we're defining it when time is 5 hours.
Water.
Yes. So approximately 110.52. Now, tell me people, what would I write down? 110 or 111? And think before you answer.
111. 111 is 0.5.
Danny? Do I have to double it? Second part. We're on part A still. Why 110? People that are answering 110.
Because you need to get a full one and you can't have.
Yeah, you can't, even though you would want to round up here to 111, you really can't. You can't have a half of an organism. So how many organisms do you have? You have at least 110, right? 110 organisms. And then you have another half of an organism, technically. Even though you really, it would be like that 110th organism might be in the middle of reproducing or splitting in half. Okay, that's where that half comes into play. Okay, so 110 organisms. Now, for part B it says, how long will it take the population to double? So what do we want to know when the population is what?
120.
200. Again, let's take a look. Here's the original population. Double that would just be 200. So what we're doing now is we're really setting y equal to 200. And what are we solving for in this case? x, or in this case,
T.
t. Remember, e is a number. E is no longer a variable in this case. E is a number. You're not solving for e. Your only variables are y, which is right here. Here's y, and here's x, right? Again, dependent variable, independent variable. Call them x, y, t, doesn't matter. But now we know that this quantity is 200, and we have to solve for t. Well, I can't solve for t still, because we still haven't learned that thing called a logarithm. The logarithm is going to allow me to solve for a variable in the exponent. But don't worry about it. What did we learn last class we can do here? Or 2 classes ago also, actually, both times. How could I figure out what t is?
Plug
I
in
did
the
this.
number. Plug in 0.
That'll give me an intercept for something if I plug in 0 under it. It gives me an intercept. Very good. On the what? On the graph. You find the intersection of 2 functions. Remember, if you want to know when this function is equal to 200, everybody go back to your graph, please. In y2, just type in 200, please. Remember this? We did this the other day. If you want to know what the x value is when some quantity equals the function value, so when 200 is equal to this function, you want to know when that happens, just set them equal and look for the intersection on your graph. And you're going to notice if you hit zoom 6, it's not going to work. Watch. Zoom 6. And you might get a little bit deterred at first, but you need to use logic and common sense. Look here. What's your starting value, guys? 100. Isn't this a line at 200? So what do I have to do to my y max? Increase it a whole lot, right? So for window, for y max, what might I make it?
I found it.
2 something, right? Something above 200, because I know I'm going to be at least 200. So let's try at least 225, at a minimum, 225. Along the x value, what did I get as an answer a minute ago? 110, right? 110. And that was for t equals 5 hours. So it's going to be something greater than 5 hours to get 200 organisms. Again, to have 200 organisms, it's going to be greater than 5 hours for sure. So my x max, let's for now go to 20. And if that doesn't work, no big deal. We'll go back and do it again. But let's take a look at our graph. There's my exponential growth function. And you see the constant function. That's the 200. And we want to find when these two intersect, right? So what should I do to my x max? Just keep going. Good. Increase it. So my x max, instead of 20, let's try 50. And hit graph. There's my exponential growth, which now you can see the curvature, can't you? Now you've zoomed out a lot. And there's my constant function, y equals 200. What am I searching for again?
Intersection.
So what do I press?
Intersection.
Or second, calculate, or trace for now. It's fine, either one, because they're both there. Number 5. Now it's going to say first curve, question mark. Just go over till you get to the general area. Again, you're doing this because there might be more than one intersection, and you need to specify which intersection you're talking about. There could be another intersection if a graph were to loop back around, right? Like a parabola, there would be more than one intersection. So we're specifying. So hit enter. Hit enter again in the area. Hit enter again in the area.
Oh, I did it with the table.
You can use your table. How did you do it with the table?
Kept plugging in numbers till I got it.
Yeah. So you can sit there. That's fine. What did you end up getting? You tried 34. You probably were a little under, right?
34.657.
Now, Jason, tell me, when you plugged in 34, though, what did you get? I'm asking.
I don't remember. That was a long time ago.
Can you go back to your table and try real quick? When you plugged in 34 and 35, tell me what you got.
197.
And then 35 you got?
201.
See that? And what Jason noticed was that he found that the value of 200 is between. That's awesome. I want you to be able to do this stuff, because we're going to have to use this technique at some point. And what he's looking at is kind of like the roots. Remember when you found the roots, you said if the y value goes from positive to negative, it has to cross the x-axis technically? That was our root theorem. So if this went from positive to negative, you cross the x-axis. Well, we're trying to cross the 200 marker, aren't we? Where does it cross? Somewhere in between. Well, that quantity is right here. Okay, so after how many hours? 34.7 maybe, because we're rounding to the nearest hour, we could say, or nearest tenth of an hour. 34.7. Okay, so for part 2 again, for part B, we're graphing y1 is our function, and in y2, we're graphing 200. And what we end up getting is exactly what we just said. That's what your graph ends up looking like. Okay, and I know it doesn't look exactly like that because I did this in GeoGebra, but there's your quantity. So your answer for this is time equals 34.7 hours. Okay, 34.7 hours. And that's an approximation. I should put approximations in. Okay? Again, these kind of questions are intriguing because you can't solve them by actually doing some algebra. In a day or in a few days, we're going to learn how to do this by hand. But for now, we're learning how to do this on the graph, which is a good technique to use. It's very important to know how to do this. You're going to use this intersect function over and over and over again. Okay, just to get it down pat. Yes?
It's like what science is used in order to know like the growth of like materials or stuff like that.
Say it one more time.
Like, is this what science is used? You never really want to find the growth of something.
Yeah, so for example, if they wanted to know a certain point in time in which this happens, they would look at different curves and try to find their intersection value. Absolutely. Absolutely. So if you were looking at the growth or decay of a virus and you're studying it as a doctor, or say you were, somebody that was doing research, a scientist in a lab, looking at this kind of data, you're going to use these numerical and graphical techniques to come up with your answers. You can solve them by hand sometimes, okay, but you're going to see that sometimes when the functions get more complicated, it's better to do them graphically, and this is how they do that, okay? All right, let's take a look at example 2. Anybody watch The Walking Dead? Okay, I thought maybe some people did. I thought this might be a little intriguing. So,
I don't know what you're talking about.
I read it.
you don't know what I'm talking about?
I read it.
I'm very bored.
The new series
I haven't
starts
watched
December.
I haven't been doing
In the AMC series, The Walking Dead, there is So,
no make like a house.
can I get a reader actually for this, please? Nice and loud, nice and loud.
In the AMC series The Walking Dead, there is a zombie apocalypse. Suppose that at the time the main character wakes up, zombies already rampant among humans. There is a human population of 800,000. After 2 days, 100,000 humans are dead. If the death rates are exponential, A, how long will it take for the population to be halved? B, when will you be the only person left?
Okay.
Terrible scenario.
It is a terrible scenario, I know. Sorry, I thought it was interesting now. So, let's take a look at this problem. Tell me what you know. Before we get into the problem for A and B, we have to do something else, and I'll show you why. But tell me what you know about this problem first.
Well, you're starting backwards.
Okay, so A equals 800,000, right? Okay. We can talk more about how to kill zombies later, but let's focus for now, okay? I know you're thinking about something else. Ashley? Close. The rate is not 2 days, but after 2 days you know something.
The rate is 50,000.
days you have.
Wait.
Again, guys, it's not a constant rate. It's exponential decay. So the rate is, you can't say like you're losing 50,000 per day. I know you want to say that because you lost 100,000 in 2 days, right? Which makes you think 50,000 per day. But that would be a linear function that's decreasing. These are not linear at all. These are exponential. But what do you know? At time equals what? At time equals 2. What is the value of the function?
1,000.
What is it? 700,000. Why?
Because you lost 100,000.
Because you lost 100,000. What did you start with, guys?
8,000.
So, you know, at t equals 2, y equals 700,000. That's the other thing you know. You know those two things right now. And that's it. You don't know anything else. You know that it's exponential decay. But you know that it's exponential decay if death rates are exponential. So, with these two things, what I can do is start by writing, well, y equals 800,000 e to the rx. Now, instead of x, I'm going to put a t, because we've been using t for time. The Trayvon, yeah, that's why. So, the question becomes this. If I want to figure out how long it will take for the population to be halved, I need to know the rate, don't I?
Yeah.
But isn't that still unknown? So, can I use this information, though, somewhere?
Yeah.
Think about it for a second. This is t, isn't it? So I would plug in a 2 here, and this is y, and that's 700,000. So then I could solve for r.
You put x2
Okay?
RT.
Yes, so let's do that. Let's write it. 700,000 equals 800,000
Oh,
e to the r times 2. Again, all I've done is taken what this is called a particular condition. If you want to write this down, it's going to be used in calc. Particular condition. Because they give you, think about condition means. If you're sick and the doctor says, what's the patient's condition? It means what's their status, right? How are they doing? Are they alive? Are they dead? Are they in coma? You know, do they have a fever? That's the person's condition. So this is the condition of the population of humans after 2 days. This is the condition, or a particular condition, or the condition at a particular time. That's why it's called particular. Now, with that said though, the particular condition here, these two quantities help me solve for the value of r. How might they help me solve for r? What can I do now to find r? Remember, I can't get r because it's in the exponent. We haven't learned that yet for the logs. So what can I do like we did last problem? Yeah, put it in your y equals, not guess, but put it in your y equals. And take a look. What you're going to see is this. If you graph this function on the right, and you call this, here in this case, y1, and you call this y2, and you set them equal to each other, this is what you're going to see. You have to zoom in a lot. Look at my x-axis, people. My x-axis only goes from -1 to 1. So when you're doing this on your graph, and you want to do x-min and x-max, you're going from -1 to 1. And y-min to y-max, you're going to go all the way down here from -100,000 up to about 900,000. Okay, so this is a tough one to look at because your zoom feature or your window settings might have to be tweaked a lot. How come I knew to go up to 800,000? Because look at your starting value. It's 800,000. Okay, it's 800,000. So I want to find out the rate. So I'm looking for this quantity right here, r. And remember, whenever you find an intersection for one variable, what are you really looking for? The x coordinate. And it would make sense. Look at the y coordinate. Is that a rate? No. 700,000, what is that? That's the quantity or the amount of the function. That's what the 700,000 is. Here's your rate. Okay, there's your rate. You're going to notice that if you change your settings a little bit, you'll get the same answer, but your graph might look different from mine. If you didn't go from -1 to 1 here, then you didn't go from -100,000 to 800, or 900,000 rather. Okay, so that's what we end up getting for a rate. So the first part of this problem is to just determine the rate. And what do you notice about it? It's negative. Why is it negative? It's decreasing. You went from 800,000 to 700,000 after 2 days. So the rate's got to be negative because we have decay. So because of that, we know the rate. Let's go to part A now. Well, that was before part A. That wasn't even part A yet. That was just the beginning part. Okay. We want to know for part A how long will it take for the population to be halved? Okay, for the population to be halved. Well, we know this much. We know that the function for the population is going to be 800,000 e to the RT. Now we know that R is that value, we can plug it in. Again, this is the R value right here. A minute ago, we did not know the R value. We had no idea, but now we do. And we want the population to be halved. So what should the population be then? What it should be? 400 what? 1,000. 400,000. Again, we want to know when is the value of Y half of the starting value. That's what we're going to be doing right there. So, how can I solve this again? I can't solve it by hand. What can I do with this side? What can I call this?
Y2.
And what can I call this side? And I can look for the intersection. Again, I'm trying to find out the time in which it takes for the population to be halved. If your graph looks kind of weird, you're going to have to start messing around with your zoom features. And think about what's going on now. This is going to start at 800,000, this graph here, and it's going to decay. So your general shape, when you go to it, will look like this over here. And that's what your general shape is going to look like. Again, what are we doing? We're saying 400,000 equals 800,000 e to the -0.0668 t. That's the equation we're trying to solve right now. And take a look at how we solve it. Again, we plug this into y2, we plug this into y1, and we look for the intersection of those curves. It takes some time to get used to your window settings, to get used to the ideas. You know what helps for that is practicing the homework. Okay, whenever you do this stuff, it really does help. That's how I'm able to do this stuff. And besides the fact that I'm prepping the notes myself. But I don't just sit there and know what the graph looks like. I experiment. I say, well, let me change the x values. Let me change the y values. Okay, let me see what happens. Okay? Tonight, work on the homework. We'll finish up the last example tomorrow. You do not need to do numbers, listen carefully. Numbers 3 and 4 you can leave for now. Do everything but 3 and 4. You do not need to do 3 and 4. You do not need to do 3 and 4. We're going to go over that tomorrow. Take one pass back, please.
Everybody,
You do not need to do numbers 3 and 4. Anybody else not get a homework?
No, I think this is extra now. That's something else. Hold on one second.